The two wave is set in phase when the constructive interference occurs or when the crest of the first wave repeatedly met the crest of the other waves, as you can see in the figure. Crest met with crest. So some of the wave they will add constructively as in last figure here. And the phase is set out of phase when destructive interference occurs. For example, when a crest meet with throw and we plus all together, then they will add destructively, means that flattened surface will occurs here. And as in part C, shows that when the crest meet with half crest, so they will add partially destructively, or we call as intermediate C. Constructive interference means that the amplitude increase when the wave meet, as you can see here. The amplitude are increased. Destructive interference means that the amplitude decrease when the wave meet. Okay, we add both them, so they will decrease. This one for partial or intermediate wave. Standing wave or resonant, that is the next subtopic. If two sinusoidal wave with the same amplitude and wavelength travel but in the opposite direction, as you can see in the figure, in part A it moves to the left, part B they move in to the right. So the interference with each other will produce a standing wave, as you can see in part C. This is we call as standing wave. Okay, each point represent node and antinode, and I will show the detail by the next slide. It will difference by the time. As you can see, for time equal to 0, this is standing wave, and by the time 1/4 period, okay, this one means that when the crest meet with throw, so it will flatten. Okay, the standing wave will flatten. The third one, when a crest meet with a crest, with throw meet with a throw, so it will produce. As you can see in the figure here, two wave traveling with same amplitude but different opposite direction, with different direction, so it will produce that. So standing wave have node and antinode, as you can see in the figure. This one is node, this one is antinode. Okay, a node is a point where the string stay at its equilibrium position. This is known as equilibrium position. Antinode is point where the wave is as far as it gets from the equilibrium, far from equilibrium. So this is a antinode. Standing wave occurs when both ends of a string are fixed. As you can see, fixed. In that case, only waves which are motionless at the end, means that at the end here are motionless, the string can persist. They are not where the amplitude is always 0, and antinode where the amplitude varies from 0 to maximum value here. So this is fixed at that equal to 0. So this is general equation of the standing wave. How we get this equation? Then later we derive. I'll show you how to get this equation later. The distance between adjacent and antinode is equal to pi over 2. Distance between adjacent and antinode. Okay, antinode is pi over 2. Alright, then the distance between adjacent node is equal to pi over 2. And the adjacent node and the distance between a node and an adjacent antinode is equal to pi over 4. We plus both together, so we got pi over 4. Formation of standing wave. Okay, you can see the detail here, how the standing wave form. Right? With different periods, so different standing wave form, not antinode, not antinode. This is standing. So let's have a look at the mathematical representation of standing wave. For standing wave, we need to consider two traveling waves moving in opposite direction on a string. Let's take y1 as wave number 1 in terms of xt, a sine kx minus omega t, and the second one y2 in terms of x and t as a function x and t. X is a distance, t is a time. A sine kx plus omega t. Y here is negative, here is positive. We need to consider both because in the opposite direction, one to the left, one to the right. So we add both equation, y1 plus y2, a sine kx minus omega t plus va sine kx plus omega t. Then from the cosine rule or trigonometric function, okay, check back the formula. Sine 1 plus with sine 2, so we'll get this equation. Okay, I will not show you the detail, okay, because we just simplify the equation. So we got this equation, okay, when sine 1 plus sine 2 equal to 2 sine half omega 1, sorry, theta 1 plus theta 2. So it's here, it will become cos half theta 1 minus with theta 2. So simplify, we will get y1 in terms of x and t equal to 2a. 2a is a amplitude sine kx cos omega t. So this is the general information for standing wave. Alright. Then at for a standing wave y x t equal to 0. So y here equal to 0 at x equal to 0 and x equal to L. Then satisfied when sine KL equal to 0, given that KL equal to pi, 2 pi, 3 pi until n pi. Since we know that K equal to 2 pi over lambda, so then lambda from the previous chapter, we know that lambda n equal to 2L divided by n, which is n is the integer 1, 2, 3, and so on. So remember, this is the equation of standing wave. So the wavelength 2L divided by n, or from here we can find the L as well. Just rearrange the equation. L equal to n lambda divided by the 2 from this equation here. So we just simplify the equation. So then frequencies, unit is still same. Lambda is meter. Frequencies Fn in terms of n integer, n 1, 2, 3. Then substitute the equation from the V to F lambda. If let's say we want to find the F, rearrange the equation. So we arrange the equation. So we divide by lambda n equal to 1, 2, 3, and V per 2L equal to nF1 and so on. So the frequency of the standing wave on a particular string are called natural or resonant. Spring or pendulum has only one resonant frequency, but a string may have infinite number of resonant frequency. Okay, remember, pendulum only have one resonant frequency. These frequencies are also referred to as the fundamental and harmonies, as you can see in the figure. This is the length in figure A. Then after the wave start to vibrate, so then it will produce knot and anti-knot here and knot here. And this we call as fundamental or first harmonic, known as labeled as F1. And again, it will vibrate again, produce two wave. We call as first overtone or second harmonic. F2, which is F2 equal to 2 F1, 2 times F1. And second overtone or third harmonic, F3, third harmonic. Okay, so this is a vibrating mode. So you can see here,